Okay. So we've learned inductive reactance, right? We've learned that an inductor exhibits a characteristic that allows it to store energy. And since it can store energy, we can uh, we can do pretty powerful things with it, namely like filtering certain things. Okay. Um, the way the inductor stores energy is this little thing called inductance, right? So the U or the L is pretty important. Can y'all see that? Um, and in the book, in the chapter you read, it said what causes inductance, right? Like, what is it? If you have a coil of wire, you have some amount of inductance, okay? And you can boost up that amount of inductance by putting a lot of coils really close together, right? Like a lot of loops of that coil. Um, Namely because anytime we put current through an inductor or a conductor, anything that allows electrons to flow through it, we push electrons out of that conductor. Okay. And what an inductor does is that like magnifies that by putting a bunch of loops really close together. Okay. And for, a certain amount of current that we're going through there, we build up a certain amount of electrons, in that magnetic lines of flux around that conductor. And y'all saw that when y'all built the electromagnet, right? Like the more turns you got, the closer together, the stronger the electromagnet was. Okay. So inductance is an inherent uh, characteristic of any coil of wire that's going to have current going through it. Okay. Now, it might be negligible depending on how many turns you have, but if you've got current, you've got a power source and you're going out and doing something, we've at least got one coil, don't we? One loop. So we've always got some inductance. All right. Now, in electrical, uh, if you've got things that are magnitudes, orders of magnitudes bigger, like let's say we've got 1 mega something and we've got one something. Uh, if something's negligible compared to something else, we can usually safely get rid of it to calculate things, all right? So any circuit has inductance, it has capacitance, and it's got resistance. But in this circuit right here, we've only got one loop of wire, and we've got a really big, like, let's say even at 10 ohms, that's a significant resistance. So a lot of times we can kind of ignore the things that aren't big. All right. We're about to get in where the circuit has a little bit of everything. Okay. It's got inductance, it's got capacitance, and it's got, resistance. Okay. So I'm going to try to draw this so that it's not completely stupid. All right. So once we start putting electrons through here and we start pushing them through here, like we start pushing electrons out, okay? And that takes more energy than just pushing the electron through and there not being anything in the way to push out. Okay? So some of the energy that we impart onto a conductor gets converted into magnetism. So we're storing energy through magnetism. Okay? And then once we stop, what'll happen is an inductor will cause a voltage spike as big as it needs to be. Like we're talking about infinite volts, in a perfect world, to continue that current going in the same direction. Okay? So as soon as I stop that current, those electrons are going to collapse into the conductor and cause it to keep going for just a little bit. Okay? It's going to supply a big voltage. Well, if I turn around and I start trying to put electrons in this side, the inductance is causing the electrons in that magnetic line of flux to kind of keep going this direction. So we're fighting a losing battle right there for a second, right? Now imagine that I keep changing my direction over and over again. Like the faster I do that, the harder it is for me to get current through there because I'm constantly fighting that flow. Now the first thing that happens when you plugged in that when you did the coil and you push the button, it did let current flow for just a second, didn't it? Like that LED lit up for just a second. So that was a slow. Like, let's imagine that I'm pushing that button and letting it go once a second. That's 1 hertz. That's not exhibiting a ton of resistance to me. Remember, like, if you don't remember anything, remember that inductive reactance is a positive relationship. That the higher the inductance gets, or the higher the frequency gets, the higher the inductive reactance gets. And inductive reactance we can think of like resistance in this case. Okay? Y'all cool? So what we're doing is we're storing energy. And it's a little bit harder to visualize this with an inductor than it will be with the capacitor. But we store energy through magnetism with an inductor. Okay? All right, so we've got something new. We've got capacitive reactance. And you need to remember this. All right. Now, when we've got an inverse, like when we have something under a 1, that means that we've got a negative relationship. Okay. So ignore all the funky junk in there. Ignore the 2 pi. Like, that's a constant, right? That stays the same. But what happens if the frequency or the capacitance goes up when you're under a 1? This number under the 1 gets bigger, doesn't it? Because you're multiplying by a constant. Okay? So what happens to the actual number? Like, what happens to capacitive reactance? It gets smaller. Imagine we've got a 1 over 1. What is that? That's 1, right? Let's say a 1 over 2. Is that smaller than the 1 over 1? All right, so as we go up, ... let's say we've got 100 right here. As my capacitance or my frequency goes up, what happens to my capacitive reactance? It goes down, doesn't it? Y'all understand by putting the 1 up top? So I've got a 10 nanofarad and 100 nanofarad capacitor. Oh, 100. Sorry. I got a 10 nanofarad and 100 nanofarad capacitor. Which one's going to have the biggest capacitive reactance? Pound for pound. Like, so the smaller one, right? What that really does in the real world is the smaller the capacitor, I'm going to use cap from now on for capacitor. All right. The smaller the capacitor, the smaller the capacitive reactance. Or, sorry, it's the inverse, isn't it? Okay. This isn't going to be a perfect graph, but so we've got 0 hertz and we've got 10 megahertz. Okay. 0 hertz, it doesn't matter what the capacitor is, right? Because if we multiply by 0, we get a 0. So if we've got 0 hertz and we've got something in that makes it 0 in the denominator, regardless of what anything else is, right? What is 1 divided by 0? It's undefined. Okay. A division is successive subtractions, right? When you multiply 5 times 4, what do? You add 5 plus 5 plus 5 plus 5. Okay? What happens when you divide, let's say 10 divided by 2? Yeah, so we do 10 minus 2. That gives us 8. So that gives us one thing that we subtracted. All right, then 8 minus 2, that's 6. That's 2 things that we subtracted. 6 minus 2, that's 4. That's 3 things that we subtracted, right? Now, 4 minus 2, it's 4 things. 2 minus 2, 5 things. All right, now we learned that in 3rd grade, but sometimes we get so good at doing something that we forget what we're actually doing. When I said 10 divided by 2, you immediately knew 5, but you didn't remember how you got 5, did you? That's a fair thing, right? So that's why I say memorization is one of the weakest ways of learning. Okay, because like you can forget when you memorize, but if you understand something, like you don't lose it. Okay. So what happens when we do 1 divided by 0? Like this is termed undefined, but what we're getting is like an asymptote that is like infinity. Like it's just infinite resistance. Why? Because, all right, so what do we do? 1 minus 0 gives us 1. Boom. That's one time we did that. All right, we still got 1 minus 0. Boom. I could do that forever, couldn't I? So when somebody says that 1 divided by, all right, 0 divided by 5 is 0, right? 0 minus 5, like we've already got below 0, so we got 0 and a remainder of 5. But people get weirded out when we do a divide by 0, and it's just this. Like we've got an infinite times we can subtract 0 from 1. So it's way up here, and then it swoops down pretty quick, right? So as the frequency goes up, it exhibits less and less capacitive reactance. So if we have a complex signal that has, a whole lot of, I don't know why it's doing that. We have a complex signal that has a lot of doodads going on, right? We could put it through a capacitor, and a capacitor looks like that on a schematic. And then we're just going to get the high frequency component of it, okay? Because the low frequency would get blocked. So we're seeing some power here, aren't we? Look at what capacitance is. To make an inductor, we just need a coil of wire. We need a coil of conductor, okay? To make a capacitor, we just need 2 flat conductors that are like parallel to each other. Why do they need to be parallel? Because if they're not parallel, imagine we've got this little number here, okay? We've got a whole lot of surface area right here, and we've got a whole lot of surface area right here that we could store electrons. But the distance between the shortest distance between those 2 plates, like we can't store a lot of electrons right here, can we? That's why lightning hits the tallest part of wherever it's near, right? Because you've got the sky, and you've got part right here. The only thing that's keeping that from getting down here is the distance between these 2 points, okay? So the maximum amount of charge that I can do is dependent upon that. And so like all of this right here and all of this right here is wasted because I've got this little hill right here, right? And that's where it's going to jump. All right, so we're going to play with the I've got what's called a Wimshurst machine, okay? And it generates electricity. All right, so generation is not creating electricity, okay? Generation is converting it from one form to another. All right, so can y'all see that? All right, so a Wimshurst machine generates electricity, but all it's doing is it's converting it from the electrons that we have in the air, and it's like we've got some electrons on this plate just because, we've got electrons in the air, okay? And what happens is, as we spin this, those two plates turn opposite of each other, okay? Y'all see that? I'm trying to see if it'll do it on the all right, so what happens is we take a little electron right here, and then we scoop it up with this brush, like we've got a brush on either side, okay? Now what happens is that gives a net positive charge to that little plate. Well, what happens when that little positive charge lines up with the plate on the other side? That attracts an electron, doesn't it? All right, and then as it turns, it gets scooped off by this brush. It's just a conductor, and it gets put over here. Well, then that gives it a net positive charge, right? So it's just going back and forth, like causing electrons to get attracted to it because it's got a net positive charge at a certain point, and then scooping those extra electrons off, right? All right, so now one thing about the video is once I start this going, it gets a lot of electrical noise in the air. Okay, so I'm going to start freaking out my electronic devices. So I don't have a clue as if the video will work after this, right? Because we're probably going to see a lot of like electrical artifacts. Y'all hear it popping right now? If you can't hear it online, it's popping. Like, so what happens is once it gets to a certain voltage, it can pop over. Okay, we've got an insulator in between those two things called air. Okay, and as we turn this, it's popping over. Now the closer I get it, the faster, like it's popping faster. Is it screwing up the video? Okay, but y'all get to see it, right? And y'all can hear it. Now it's going to get worse as I go. All right. Now that's because right now we're not really storing the charge as much as we can, because the only stored charge that we can do is between those two balls, right? So what I'm going to do is I'm going to turn these two little things down, and what they do is they engage these Leyden jars, okay? A Leyden jar is a capacitor. It's the first way that we learned how to store energy through static. And all it is a conductor, a plate, and another plate inside of a jar. And they're circular. They're a tube, right? But the glass of the jar, like there's a metal plate on the outside and a metal plate on the inside, okay? Now what happens is we start pushing electrons onto those plates, okay? And since they've got a big flat surface, we can store a lot of electrons there. If we had a little part where it was closer together, it would negate all the other plate, right? Because the only charge we could store was at that little crooked part, you know? Okay? That makes sense when you think about the hill getting hit by lightning more, right? All right, so now as I start charging up, like, is the video completely off? Whenever it pops. All right, so now I can get, I don't know if it's 10, we'll have to look it up. Y'all look it up, and next week tell me how many millimeters per 1,000 volts, right? But as I pull this out, like we can get like near about 100,000 volts off of this thing, right? Now those Leyden jars don't change. Y'all hear it? It took longer for it to charge up, right? Because it takes more electrons to it takes more charge to jump that gap, and so we're able to charge it up more, right? All right, now watch this, right? So all we're doing is scraping electrons out of the air, right? I'll turn it a little bit more so y'all can see it, right? Are y'all able to see it? Now, as I pull that up, I'm able to charge up more because the gap between them, like that gap stays the same. They're parallel. So when they're perfectly parallel, you can store up a whole lot of charge. Okay, and then we've got these two little uh, balls that we can put closer together so that we kind of concentrate that charge. Okay, and once it gets big enough for it, now if I keep turning this, what'll happen is like I'm starting to smell ozone, like I'm breaking down the atmosphere. Okay, when you record a lightning strike, usually it'll be like 4 or 5 different lightning strikes hitting the same spot really quick over and over again. Because as soon as you make that ozone, you actually make it easier for it to get by. Ozone has a less it has less insulator characteristics. Okay. Yeah. Is it still popping the screen? It's probably going to get even worse. All right. So now, like, I'm able to pop over easier. I'm not able to get as much of a charge because the ozone is making a gap. But it also makes it so that I can get a little bit farther out. All right. And as I get a little bit farther out, y'all can tell by the size of the little lightning strike that I'm getting more powerful, right? Because I'm able to charge up enough before it actually pops over. It shouldn't scare you unless you have a see how big we can get it. All right, so now I've got the gap so big that these are closer together than that is, like the two brushes. But when we do get a pop up there, it's a big chungus in it. All right, now this will pop you, and it will, keep a pretty good charge on it. So you want to kill the Leyden jars, and you want to put these together so that any built up charge can dissipate. Okay. Did it kill the whole thing? Oops. All right. So did it kill the whole, like, it just did it? Okay. So that does bring up some good points about electrical noise. Like when you've got something that's generating a whole lot of electrical noise, the little electronic components that you're going to be dealing with have problems. Okay. All right. So sometimes it's easier to recognize storing a charge in the capacitor. Okay. Where I said think of the inductor as a flywheel, right? A big heavy flywheel. And if we can store energy through movement. All right. So that's kinetic energy. Capacitors are the opposite. You store energy through static, which static means not moving, right? Potential energy. All right, so you can think of a inductor like a flywheel, and I like to think of a capacitor like a water tower. Okay, let's say we've got this big old lake, right? And let's set Smith Lake, so we'll put all these dead bodies up in there. Yeah, is it not showing up? How about now? All right, so we got Smith Lake. We got all the dead bodies. Couple of cars. All right, there's just a ton of stuff in Smith Lake you don't want to know about. There's graveyards in there, like when they flooded the valley. But water you can store energy in water by how high it is, right? It wants to get down to sea level, right? Well, what we do, we can pump this. Let's say we've got a pump and it goes to your house, right? Now, that pump might be powerful enough to supply the amount of water that you want for your bath and stuff. But what happens is everybody gets home and everybody takes their bath at like 7 o'clock at night. That pump's probably not going to be able to supply all of that. Let's say it can supply half. So what happens is we'll pump up to a water tower. And so like at noon when nobody's taking a bath, right? That the pump could be still working. And whenever we need that extra water, it had been working throughout the day so that it can supply what we need without having 50 million pumps, right? So it's kind of like the cafeteria lady. Like if she cooks your cafeteria food right when you're there, it's going to take forever to get your cafeteria food. She can't feed everybody, right? So she spends all morning, you know, with a lot of love preparing your meal so that when 500 kids come through, they've got it, okay? All right. So, you know, high voltage, low voltage, and distribute that electricity over a great distance, right? But it is not really good for like electronics, okay? Like when we do electronics, we usually deal with like ones and zeros, if it's on or if it's off, okay? So we like to get our power back and forth, like to our house from the generation plant through alternating current, because we can boost up the voltage real high and we can get the same amount of power out of it with a high voltage, low current, but we don't have as much line loss, right? When y'all did the P equals IE and you started looking at like if you were missing an I or an E, power also equaled what? Like if we were missing the I, what is I? All right, so we've got E over IR, right? So if we're missing the I, that's E R times E, right? So P also equals E squared divided by R, right? What if we were missing the E? All right, so we've got an I, and then what is E? I times R, right? So power also equals I squared R. If we have 10 ohms worth of resistance in a wire, we can get the same power through that with a high voltage low current or low voltage high current. But look at how resistance interacts with either, right? Like, so if we have a high current, that line is going to lose a lot of volt or a lot of power through that resistance. So if we have a choice, we want to do high voltage, low current. Only way we can do that really is through transforming. Transformer is a really efficient way of converting power back and forth. All right. So we've got a sine wave. And that's really good to get us power to our house, but then like practically everything that we've got depends on, like even my light bulb. Back in the day, the light bulb was one of the things that used AC just raw, but I've got a lot of LED light bulbs. What they do is they call it rectification, and they put it through some diodes, right? And it converts it into something that looks like this, okay? So that bottom part of the line, it flips it up. So it's a changing voltage, but it's always above the zero. So it's not an alternating current anymore, right? If this is 60 hertz and you flip it up here, what do you've got? You've got something that's double the frequency. So 120 times a second, you're going down to about 0 volts, right? All right. So we want something that looks kind of like this. So we've got 0 volts here and some voltage up here. We want it as smooth as we can get it, right? So we'll put it through a capacitor. So let's say we've got our sine wave. We put it through our, like a bridge rectifier, right? And in AC, or in solid state, you'll learn how to build one. And then we'll come out, because it's still got this little number here, right? And we want to smooth that out. Okay? And we'll put capacitors there. Okay? Think of those as little water towers. Okay? So what happens is, out of that bridge rectifier, we get, something where the negative going part of the sine wave is flipped up top. Okay? When we get to a certain point, it takes all that extra, like, so it would have kept going up, right? And it starts charging up and starts putting electrons on a plate of capacitor. Okay? So it starts smoothing off the top of it, right? Or cutting off the top of it. And then whenever it starts trying to dip down, right? Those electrons go out to supply a little bit extra power, so it doesn't really dip down anymore. We've got something, so like this top part of the signal, it's charging up a capacitor, right? And then this bottom half, or bottom part of it, it is taking that extra charge and it's holding it there, right? So that, like, the extra electrons, instead of dipping down, we're using that reserve. Okay? So by putting capacitors, like, in parallel across there, we're going to start getting, what, might have, some noise on it. But it's starting to smooth out into, like, a straight line. Like what we think of as a direct current. Okay? Y'all follow this? So what it does is smooths it out to look kind of like that. Okay?
Go over what it does to, because I understand the portion where it's going up and it's positive. Explain what it does when it's negative again.
Yes. All right. So when it goes up above this point right here, right, it starts taking those extra electrons, and instead of letting it go up any higher, it starts storing up, let's say, water in the water tower. And then that gives us extra electrons so that whenever it starts dipping right here, right, we've got electrons in those capacitors that are going to help supplement the electrons that we don't have when we do that dip. Okay? Does that help any, or does that clarify any? All right, so when you look at a measurement and you see peak to peak, and then you see what's called RMS, right? RMS means root mean squared, okay? Taking the square root, mean is the average, all right, and square is a square. If you add a sine wave together with itself, like, so it's going around 0 volts, even if it goes up to 1,000,000 volts and down to 1,000,000, for every million, we've got a negative million, right? For every 500,000, we've got a negative 500,000. So that always winds up being 0 volts when you average a sine wave together that goes around 0 volts. That doesn't give us a good indication of the amount of power that's there for us. So we use what's called root mean squared. All right. So we average it, and what we do when you do a square or something, it's always positive, right? 2 squared is 4. Negative 2 squared is 4. Negative times a negative is a positive. So we effectively, when we square it, we make it bigger, and then through math, we flip that other side. Let me set that to my boss real quick. It's not, so I'll call him back. All right. So through math, we flip that side up by squaring it. We average that, and then we take the square root of it because we made it artificially big to make it flip up, right? And that gives us some number, I think is at, near about 70% of wherever that went up. So let's say around 70% of that. Okay. Cool. And when you read on a meter RMS, that's a better reading of the amount of energy that you've got to use. Okay. Think about it this way. This number right here is what happens if, let's say, these were 2 hills and I want to build a house up here, right? If I took a bulldozer and I pushed all of the dirt right here and I filled up this hole, and I pushed all this dirt and filled up this hole, right? So RMS is the DC equivalent of how much power that AC signal can do. Okay. And it's a better indicator of the energy that I can do or that I have available to me. That's exactly that's what we're doing with these capacitors, is we're converting that sine wave into a straight line, right? And we're basically taking those peaks and scooping them into the valleys until we've got a flat surface. Okay? All right. So what are we going to do? We're going to do a lot of stuff before we're done. We've got a lot of capacitor stuff in our labs. All right. And inductors have fallen out of favor for using them for electrical uses unless we absolutely have to, because they're heavy, they're big, they cost a lot of money to make because they've got a lot of copper in them. So we do a whole lot of things with capacitors. Okay. They're cheap, they're easy to make, and we can practically do most of the stuff that we can do with an inductor with a capacitor by flipping it. Okay, by changing how we put it in a circuit. All right, so capacitive reactance. You get the point of how that works. As the capacitance goes up or as the frequency goes up, the resistive nature of that capacitor goes down, right? It lets things through. I've said this a couple of times. The way it works is, in DC, I'm just putting electrons over here, and I've got a gap that's too big for that to jump, okay? So I just fill this up with electrons. So when we first turn on a circuit with a capacitor, we might see what we think is a little bit of current, And that what that is as I'm filling up this plate, the electrons on this side are getting expelled. Okay? But once I fill up that plate, there's no movement anymore. Okay? But it still holds true that a change of current or a change of voltage does that, right? Like, so whenever I push that button and so it goes from low to high, I actually have a change. And so I do see a little bit of current flow when I first flip that switch. That's it charging up and the electrons on the other side getting out of town. Okay. And then all of a sudden, my current stops and it looks like an open there. I've got a circuit and it just cannot get across there. It's got an open. As my frequency goes up, that means that I'm going in this side and then I stop and I start going in this side. So I'm going back and forth, right? Alternating current. So I charge up one side and then I change direction and I start charging up this side. Now it's a big enough gap that my electron cannot jump it. But it's a little axis of influence, right? It's a little cloud of, negativity. It repels other electrons. And that gap's not big enough that it can't, like, that repelling force cannot get across it. So as I knock an electron in this side, it doesn't jump that gap, but its cloud makes an electron over here leave, right? And so I'll start charging up one plate. And then as long as the frequency is high enough, like if it's slow enough, I'll charge up a plate and then it won't be able to go, right? And then whenever it changes direction, it'll start going again and then it'll fill up and it can't go anymore, right? So there's some amount of resistance there. But as I speed up, what happens? For every electron that I put in, I didn't fill up that plate yet. There's an electron coming out. And then I change direction before I completely deplete that other plate to start filling it back in again, right? And so now an electron goes out this way. And when we're looking on the outside of that capacitor, it doesn't matter that the same electron that came in isn't the same electron that came out, correct? So we do have that gap. I want you to realize that it does keep the electrons on their own side, okay? But if we have a high enough frequency going back and forth, we put an electron in and it ping pongs another one out because it's repelling that one across that gap, okay? Kind of remember that capacitive reactance, okay? 2 pi, again, oops, it should have capacitance here. 2 pi times frequency is a speed, right? 2 pi is 100 or 360 degrees. It's going in a circle. Frequency is how many times it's going in that circle, right? So how fast that sine wave is going, right? This versus that. Okay. Let's look at capacitance. Capacitance is how much charge we can store through static. Let's say that. What was inductance? How much charge or how much energy we could store through magnetism, right? What makes a capacitor a good capacitor? The surface area of these plates. So I can't draw in 3D, right? I've got these 2 plates that are across from each other. The surface area is going to give me the amount of electrons I can put on it, okay? The distance between those 2 plates, Okay. And how strong the dielectric material is in between them. Okay. We do have some air gap capacitors where we've got really stiff plates that are across from each other. Most of the time, like a lot of the capacitors you'll use will have like full. It'll be flat, but we'll put like a piece of wax paper, old impregnated paper, and we'll roll it up like a fruit roll up. I showed this class opening up a capacitor, haven't I? So the strength of the dielectric, that's going to make it harder for electrons to get across there. Because if we get an electron across here, we've got a problem. Okay? We can't store as many. And in doing so, we damage the capacitor and we usually just blow it up. Right? The distance between those and the surface area. Okay? So that makes sense. Like the bigger the water tank, the more water we can store up there, right? On page 32 of the here, it's gonna have like when we talk about when I said 1 over 2 pi times frequency times conductance, I shouldn't have put a C there. I should have put a F there, a big F. All right. Capacitance is, or I could. Capacitance is measured in what's called farads. Okay. Now, 1 farad is huge when we're talking about stuff. We need to convert it into farads to do this. All right. Now, capacitors, like even big capacitors, might be, let's say, 47 microfarads. Okay. Now, when we did inductance, we did pretty big Henrys, like where we did like a full Henry or something. Very rarely are you ever going to do a full farad, okay? So it's got a chart where it's got farads, and we've got 0.001 farad is equal to 1,000 microfarads, and is equal to 1 million nanofarads. Okay, we go down to picofarads, right, which is a billionth of a farad, or a trillionth. Add 3 more to that, but see, we're only at 0.001. So 1 farad would be what? So we move that 1, 2, 3. 1, 2, 3. Or 1, 2, 3. So that'd be 1 million microfarads is equal to 1 farad. 1 billion nanofarads will be equal to 1 farad, and 1 trillion, I believe. The way I remember this right here, this billion, is nano means like, I think a 9. So that's 9 zeros, right? Cool. Micro, I think a million, 1 millionth. All right, so if I give you a 47 nanofarad what is it equal to in farads? I guess pico is 1 billion. They left off nano. No, it is 1 trillion. Sorry. It's still talking about that 0.001. You'll understand when we get in there. It is 1 trillion. So all right, so we've got 47, and then a billion of those equals 1 farad. Okay, so a billion, we need to move 9 times, right? 9 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the number we need to put in when it says 47 nanofarads. Okay? If you just put in 47 into that equation, you're going to get it wrong. Okay? Now, I'm doing something for those who watch the videos and those who come in. On the questions, I say do all of them. And the people who don't watch the video or don't do it, they're going to do all of them. Right? I just want you to do the first 5. People are going to ask me questions. Do we need to do all of them? I'll be like, what's it say? Now, those of you who've watched the video and those of you who are in here, you know that I mean what did I say, which is do just 5 of them. Okay? So the people who don't watch it, they're gonna have issues, aren't they? Let's pull this up real quick. 16 is the one where we start talking about capacitance, right? Y'all got the book? I think it is 16. Let's see what's next on our little list. Unit 16. All right, so on the actual unit, do the review questions and practice problems at the end of the unit. Look up how to make a table in a document if you're having trouble formatting your answers for some of the questions that have tables. So if there's a question that y'all need from 1 through 5 that has a table, if you need help, do that. All right, so let me edit this because we were late on that week. We had a thing out, so I want to take the few extra days off. Instead of a few extra days, what I'm doing is those who are actually, cognizant of and doing what you're supposed to, just do 1 through 5. I think I've said this 3 times, just do 1 through 5. If you ask me how many are we supposed to do, I'm going to go, what does it say? When I say what does it say, I mean what did I say in the video, but you're not going to know that if you didn't watch the video. But I'm saying this a bunch of times, so that if you watch the video, it should be apparent. Just do 1 through 5. If you're not watching the video, then you're probably going to do all of them, and it's going to take you forever. And I'm not going to have any sympathy, and I'll be like, did you watch the video? And you'd be like, yeah, even the part where I said just do 1 through 5. All right, but I'm not going to tell them that until after they do all of them. Does that sound fair to y'all? That sounds pretty fair. All right, I'm going to give that until Sunday night. 11:59 p.m. All right. November 7th. For lab, I'm going to get you to do this is going to be an ongoing thing. All right. Like, so for the next 2 weeks or so, going to do page, read it too, 32, 33, 34, 35, 36, and then I don't know how long it's going to take y'all. Some people it takes like no time. Some people it takes like forever. So I'm not saying that you have to finish it this go round, right? Like this will probably take up this week and then next week because it is all capacitors. When you go on to 37, you need to go back to page 19 and build the 555 black box. Okay. All right. And then once you do that, wait, that should be 37. You go back to 19, build the black box. All right. We'll hold it off there, and then I know that'll give enough things for y'all to do for this weekend, next week. All right. This is where it's going to get hairy. I do want to explain something to you real quick that's going to make your life easier. Okay. What time is it? It's about 9. All right. So I'm going to draw a circuit real quick. It says plus 9 volts. I did. Thank you. Okay. Couple of things to note. It does give you like 46 and 47 as being terminals to go to that button, right? But then it does in the note say to put this on T25 and T26, the capacitor, right? You need to get I die, I love y'all. To my family, I do too. Oh. When you have a lisp as bad as mine, sometimes you could choke to death on your own spit, right? It's not fun. I hope that's not the way I go. I hope it's eating a quesadilla, like, you know, doing something crazy cool. This is slowing you up, okay? Like trying to put it in the exact terminal. When you do a schematic like mine, right? Like, I just look at the schematic and I don't care where it's, because the breadboard doesn't care. If I've got a row and I need to attach something to a capacitor, right? I don't care what row it's on, all right? So I would follow through and I'd go find my 9 volt output. And then I'd put a wire to 46 that actually works because it's telling you what button to put it on, right? And then I'd come out of 47. I'd go to any random hole and hook up a capacitor, okay? Now, some capacitors are what's called they have a polarity about them, okay? Just like a diode, when you see this little line right here, that's the cathode. That's the flat side of the diode, right? Or the short leg, okay? It only goes in the circuit one way. An electrolytic does too. When you get bigger into like the nanofarads or the microfarads, I'm sorry, most of those are electrolytic and they are polarity sensitive, okay? Most of the time, let's say they look like a little canister like this, and they'll have a little line down it. They'll have a negative that's just going down the side, okay? That means always put that leg toward the negative part of the circuit or you're going to pop that cap, okay? Like not the cool type, like when I'm defending my set, right? Like you're going to pop that cap and it's going to go in your eyeball. So make sure you got safety glasses on, okay? But when you've got the little U here looking thing, that means that that's the negative side of that capacitor. It might not have a positive thing on it, but this one does, all right? The cap probably doesn't have a positive designator. It'll just have the negative, and that's how you put it in, is the negative toward ground, okay? It's a lot quicker to ignore when it's like put this in T25 and T26 and you're counting and doing all that. This is the time where you should start being able to go, all of those rows are equal, right? Just start from one side and start wiring it up and get good practicing on that, okay? Y'all got any questions? Y'all feel good about this? Like we're about to start, like what this will do, when I push that first button on the left, we'll get a little charge, right? I can also push that button in between and I can take that charge that we used and dump it back through that diode. Okay, so we're charging the capacitor, we're discharging it. Read the stuff in there because that's a lot of what we're going to talk about next time. Y'all have a good evening.